Okay, good evening, Professor David J. De Las Reyes. Okay, the date for today is September 20, 2023. The time is 8:25 p.m. Okay, my topic for tonight will be a long video format discussion, and this is one of the long video formats under my channel. It's alternating current machines. And I am now on lesson number 17. So for those of you guys who are following my AC Machines lecture on my channel, we are now on lesson number 17. And the topic for lesson number 17 is the open circuit test of the transformers, and this is used in the so-called determination of the core loss. Because one of the losses for a transformer is actually the so-called copper loss and the core loss. Copper loss is due to the windings of the transformer, okay, because there is no such thing as a perfect transformer, perfect winding, and the other loss is actually due to the core loss. Core loss meaning it is the part of the transformer in which the primary and secondary windings are wound. There are losses due to it. Okay, let's proceed for tonight. My topic for tonight will be a long video format discussion on alternating current machines, and I am now on lesson number 17. We are running smooth. So actually lesson number 1 to 17 is concentrated on the study of transformers, the different concepts plus the different computations of the parameters for the good operation of a transformer. Okay, let's proceed. AC Machines, lesson number 17, and the title of the topic is Open Circuit Test of Transformers. The last time around, the topic was actually a problem involving the so-called short circuit test. Tonight, I will be presenting the concepts and the so-called circuit diagrams on how to perform an open circuit test for transformer. Okay, let's try to bring out the figure. For the figure on how to perform the so-called open circuit test, actually, we do this once in the laboratory. Okay, when I took up my engineering, we perform this one in the laboratory. So this test is actually a very dangerous one because the primary side or the high side of the transformer is open. It's open, right? So just in case you touch it accidentally, you will be electrocuted. So there is actually a danger in performing the so-called open circuit test. Okay, let's try to bring out the figure. This will be the transformer, single phase. Right? Single phase. Number 1, this is the designation for phase. So this should be for open circuit test, the connection is the reverse of the short circuit test. For the open circuit test, this is the primary side. We just interchange it because for the open circuit test, the instruments are connected on the secondary side. Okay? For open circuit test, this is secondary side. So the wattmeter and the voltmeter is connected on the secondary side. What is open is actually the primary side, the primary side. That's why there is a caution here. Okay? HV, meaning high voltage. And since the test is actually open circuit, okay, these terminals here are open. So just in case, okay, you touch the two terminals accidentally, oh, you're unlucky. You're an unlucky person. Why? You become the load of the transformer. Okay, you will be electrocuted. right? So it's a very dangerous thing, this open circuit test. So this is open. The applied voltage on the secondary is the applied voltage on the secondary is the rated secondary voltage. So just in case you touch this one, okay, you will become the load, and I don't know how much current will be going into your body. So that's why under the annotations, annotation number 4, just be careful not to touch the primary side when you are performing the so-called open circuit test. Okay, let's continue. So the instruments connected on the secondary. Okay, I am repeating. The instruments are connected on the secondary. What is open is actually the primary side. Okay, the high voltage side. So if you got a transformer which is 2400 and a 240, meaning to say you will apply 240 here, right? Of course, the ratio transformation is 10, right? The primary side is open, so supposed to be, if there is a load over here, the voltage here is 2400, right? So just in case you touch this one, okay, if you apply 240 here, whether you like it or not, there should be a 2400 over here. So just in case you touch it, you are touching a 2400 volts and you will be electrocuted. You are dead immediately, right? So for this open circuit test, this is a very dangerous one, and there is a caution and what they call this, not to touch the primary side when the secondary side is energized. While performing the experiment or the open circuit test, okay, make it a point that don't touch the two terminals of the primary side. Okay, let's continue. One side is open. It is the primary side, right? Oh, I will go back to the instrument. This is the wattmeter and this is the voltmeter. This voltmeter here will measure how much voltage is inputted on the secondary, on this terminal here. Okay? If we are on the secondary side, on the laboratory, there should be a voltage, maybe around 240. We could produce 240 on the laboratory side. But for a 2400, that's very high. That's why open circuit test is not actually performed by injecting voltage on the primary, okay? Then you let the secondary open. So we reverse that one. So we could have available voltage at the laboratory. We use the input terminal to be the secondary, and what is open is actually the primary. Okay, let's continue. So this is the wattmeter. What's the use of the wattmeter? The wattmeter actually measures the core loss. Okay? Core loss. Core loss meaning it's due to the core, the lamination, the core, the part where the primary and secondary are one. It's the core, right? So whatever reading on the wattmeter is actually termed as the core loss. So if you hear open circuit test, it means it measures the core loss. Oh, that's the only thing it could measure. Plus the other one, the one that could be measured by the no load test is actually the no load circuit parameters designated by RO. There should be resistance and reactance. This RO here is the current due to the hysteresis. It's a real part, right? And this XM here is the current due to the AD current. It is this. Okay, so the vectorial sum of the hysteresis current and the AD current, which is termed to as the exciting current, is actually the no load current. So for an open circuit test, we are finding for the core loss plus the value of RO and XM. Okay, that's the only one that we could give. Because from the short circuit test, okay, we computed or we brought out actually RA, XA, and ZA. So those are termed to as the so-called copper loss. So for the open circuit test, what we are looking for is the core loss plus the value of RO and XM. Okay? And that completes the total copper loss for a transformer. The total copper loss for a transformer, no, the total loss for a transformer is due to the windings plus the losses due to the core, meaning the lamination. Okay, let's continue. One side is open, usually the primary. Okay. The other side, which is the secondary, is connected to an AC source where the voltage is the rated value. Meaning, this secondary side, you inject a voltage equivalent to the rated value. So if this transformer is with the voltage specs of 2400 and 240, the rated BS here should be 240. So maybe in the laboratory, there is a 240 volts. Okay? If there is a higher one, we could adjust that one to a 240 by using a rheostat. Okay? So this is open, and we inject a rated voltage on the secondary. That's number 2. What's number 3? Oh, this is just a side note. The current on the secondary is extremely low, 2 to 10% of IS rated. Meaning, the rated secondary current here, IS, for this no load test, okay, what will come out for the current here is very low. According to this side notation here, it is only with the value 2 to 10%. Okay, so if the secondary current is assuming 400 amperes, during the experiment, what will come out that the value of the current on the secondary will only be in the range 2% to 10%. Oh, that is the side note. Oh, this is the most important thing here. When the circuit is energized, meaning this is open, we apply the rated voltage on the secondary. Okay? Great care should be taken not to come in contact with the high voltage side. High voltage side meaning, because if this is a voltage rating of 2400 and 240, this should be with the rating 2400 and this is 240, right? So if this is energized with the 240, whether we like it or not, there should be a 2400 over here. Okay? And according to this note, at the time of the energizing, make it a point that do not touch the top terminals over here. Okay? Don't come in contact. Right? This is 2400 and you are touching it, you will be electrocuted. Okay? I don't know how much current will pass through your body by just using voltage is equal to IC. Right? If this is 2400, assuming your body got an impedance of 1 mega ohm, actually you could compute for the current passing through your body. It will be 2400 divided by 1 mega ohm. And you know how much current is that one. It might burn you. Okay? That's the very important thing under this annotation. This will be annotation number 4. Okay, I will try to repeat it. When the circuit is energized, great care should be taken not to come in contact with the high voltage side. Okay? That is for the safety of the so-called experimenters, right? The one performing the experiment. Number 5. Before taking measurements of the wattmeter, of course, you apply 240 here. Okay? How come you know it's 240? There is a voltmeter here. So if there is a rheostat here, you adjust the voltage to 240. As soon as the voltage becomes 240 over here, okay, stop injecting the additional voltage. It will just be only up to 240. Right? Annotation number 5, before taking the measurements of the wattmeter, the impressed voltage be adjusted to rated value. Okay? Meaning to say, before you will take the reading here, which represents the core loss, just be sure that the impressed voltage here is the rated value. Okay, it should be the rated value. It's not less than, it's not greater. It should be the rated value. Okay? And according to number 6, it is at this voltage that the proper core loss is measured. Meaning to say, under the open circuit test, if the applied voltage here is the correct rated secondary voltage, what will come out for the wattmeter reading is actually the proper core loss. Right? It's the loss due to the lamination or iron core of the transformer. Number 7 is just a side note. The core loss represents are actually got two components: the hysteresis and eddy current. Okay, this is the hysteresis and this is the eddy current. The vectorial sum of the hysteresis and the eddy current is actually the no load current. No load current. I will try to resist one. Okay. For the hysteresis loss, this is just a side note again. Hysteresis loss, this portion here, to minimize, use high quality magnetic steel. Meaning it will be on the property of the core that you will be using. So to minimize the hysteresis loss, use high quality magnetic steel. And another side note for the losses, for the eddy current loss, to control the eddy current loss, I place it here, controlled by laminating or slicing the core. So as you try to notice it, the core of the transformer are actually 10 slices, right? It's like this, many slices, okay? They are bundled into one. To, according to this side note over here, to minimize, the loss due to this is actually eddy current, and to minimize that losses, okay, we must have to laminate or slice the core, okay? Some 10 plates that we merge into one, right? That's the meaning of slicing the core. What's next? Number 10, this is just a vector summation. The total impedance at no load will be capital letter R with the subscript O plus J, capital letter X with the subscript M. This RO here is referred to as the hysteresis loss. Why hysteresis loss? That is just resistance. If you try to multiply this by I square, that will now be I square R sub O, and that is actually termed to as hysteresis loss. And again, if you try to multiply this X of M by the square of the current, that is termed to as the eddy current loss. So under this open circuit test, we could measure RO and X of M, and if we try to multiply that by the square of the current, that now represents the hysteresis loss and the so-called eddy current loss. This is just a vector diagram of the flux and the no load current. The flux is this one, okay? The real part of the no load current is IHA, it's the hysteresis current, and the imaginary part, because this current here is different from this one. How this one acts is different from this. This is real part, this is imaginary part. This is in phase with the mutual flux. So the vectorial sum of Ix plus IHE is actually I no load. So if we try to bring out the equation here, I no load will be equal to IHE plus J I excitation or eddy current, right? This is the real part of the no load current. This is the imaginary part of the no load current. They are not the same. This is due to the resistance, and this is due to the reactance. And this represents the no load current. So if we try to multiply this no load current by the value RO and X of M, that now represents the hysteresis loss and the eddy current loss. Okay? So this one is actually what we call this measured by this wattmeter. Okay? Okay, that's it, guys. That's the proper way on how to perform an open circuit test for a transformer. And in summary, am I still on camera? And in summary, open circuit test is actually a test for transformers to determine the core loss and the value of RO and XM for transformers. Okay, I will repeat it. To perform this open circuit test, the primary side is the high voltage side is open. We impress the rated voltage on the secondary side. Okay, so as soon as the rated voltage is impressed over here, take the rating on the wattmeter, and that reading on the wattmeter is termed to as the core loss. Okay, and this core loss is just as a side note. Okay, got to what I call this component. It's the RO and XM. If we try to multiply this by current, that now represents the hysteresis and current loss. So meaning to say this core loss here is actually the sum of the hysteresis and eddy current loss. Okay, good evening from Los Angeles. This is Professor David J. De Los Reyes.